Okay, guys, welcome back. Back to the way that wanted to see how can we implement the operator itself. So in order to talk about the query processing algorithms or the actual algorithms, we can classify them based on the following criteria. The way that how many times you're going to access the data or read the data. Okay, one pass algorithm, two pass algorithm, or multi-pass algorithm. Okay, so what do we mean by one pass algorithm? You're gonna hear this one more frequently, or if you take many papers about to say the query optimization, or even in this class. So one pass algorithm, that's means the way how many times I'm going to access the data or read the data. I'm not talking about the reading. So if you access only the data one time, that means you read the entire block, then done. I don't care about the way that you read this one, either one at a time or maybe a sequential. The most important thing, I'm going to read this one only one time. Access the entire relation one time. So read the input relation just once, which is going to use, the lowest disk input out operation, because in order to read the data, BR if the data is clustered, TR if the data unclustered. This is the cost, right? This one is I have the problem with this one. You have the highest memory space requirement, because generally speaking, the one pass algorithm, most of the case you need enough data or memory or in the buffer pool that allow me, or can fit. One relation, the entire relation can be stored on the disk, let's say in the buffer pool. Okay, because I'm gonna be from somehow relation one memory. That means I'm not gonna access the relation anymore. Right? The second one, or second algorithm, can be it's called the two-pass algorithm. So in this case, we're gonna read this or access the data twice. When you say X, I mean only reading. So just speaking, this kind of protocol is gonna have two parts or two phases. The first one, we call this one preparation. You prepare your data somehow, you partial sorting, etc. Partially sorting your data. I'm gonna show you an example a few slides later, a few minutes later. Sorry. So you gotta perform the phase one. You gotta perform some preparation, your data preparation step. Then so that you read the data one time, then store the data in the disk back. Then after that, you have to read the data for the second time in order to perform the final step. So here in most cases, access the data is gonna be 2BR if the data is clustered, and it will be TR plus BR if the data is unclustered. So why this is the case if the data unclustered? It's going to be cost be TR plus BR disk input out operation if the data is unclustered. Why it's not 2TR, for example? Why? So if the data is unclustered, assume the relation R is unclustered. So in order to read the entire relation R from the disk to the memory, what's the cost of this? How many disk input out operation you need to perform? You cannot say BR. Yeah, it's gonna be TR, right? Because for every single disk input out operation, it's allow you to read only one tuple from this relation. I want to read the entire tuples of this relation. So it means I'm gonna use the TR with the total number of tuples of this relation, right? So for the one read, or the first read, it's gonna be TR. Okay? This is the first step. Somehow we're gonna deal with this information being get stored now next to each other somehow for the first read. So now it's gonna be the data is not unclustered anymore for this, because remember this is two pass. The first pass, you're gonna read the data. If it's not clustered, you definitely when you store the data, you're gonna store the data next to each other. So it's gonna be clustered data. In order to read this one for the second read, it's gonna be cost BPR. For each disk input out operation, I managed to get all the tuples that's stored in this block. Since we have, for example, my relation can be stored in 100 blocks, so that means in this case, I need just to perform 100 disk out operation. So it's clear why this case. In the cluster, it's going to be two passes, one TR plus one PR. And of course, it's a cluster, that means I need just to perform two PR with the cost. I need just to read the relation twice. How many blocks you're going to read? PR plus PR. Okay? I will assume it's okay. Good. The multi-pass algorithm. Now we're going to read the data more than twice. 3, 4, 5, it depends. So the same structure. Assume that you're going to read the three, say, pass or multi-pass. Okay? So in this case, 3, if the data clustered, so I'm going to read the data 1, 2, 3 times. Each of them is gonna cost me BR. So the total is gonna be 3 BR, right? If the 3 pass here, the data unclustered, the first one, most of the time you have to read this one TR. The second and third phase, generally speaking, most of the case when you read the data first time, when you store the data, I'm gonna store it next to each other in a cluster format. So it's gonna be PR and the PR here. So the total here, the cost to read this whole relation 3 times TR plus 2 multiply the PR with the number of blocks plus 2 multiplied times number of blocks plus the total number of tuples in this relation. Okay? Well, I'm going to go, I will revisit this one later, but just to keep you in mind, what you mean the unclustered and the cluster. How can you compute the cost? And of course, it depends on the algorithm in general. What the algorithm is going to do in the phase 1. What it's going to do with the data. As I mentioned, most case scenario is going to store, once you're done from the phase 1, it's going to store the data in the clustered format. So, of course, the general guidelines on order picking an algorithm. If you have sufficient memory to run one pass algorithm, do it. So it depends on the value of M, which is going to be the number of buffers of the memory, of the pages of blocks available in the memory in order to allow me to use this algorithm. So if the data can be a relation, for example, if the M, let's say the PR, is less than or equal M, yes, do one pass, for example. If not, what if the data, the problem right now, why you need 2 passes, 3 passes, why you need multiple access to the data? Because the size of the relation cannot fit in the main memory. That means I need to find a way in order to handle this situation. So if somehow you're gonna read the data multiple phases and partially perform the computation until you end up behind the final result. Okay? So if there's a sufficient memory to perform 2 passes, do it. If not, that means sometimes you're going to go multi-pass. So each algorithm right now, starting, I will introduce the first one, and for each algorithm, I'm going to show you that what the constraints associated with this algorithm. We have some limitation with the number of, with the size of that I can use in order to perform this operation. Okay? First, I'm going to talk about how can you perform sorting algorithm. This is very important. I'm going to show you the 2-pass multi-way merge algorithm in order to allow me in order to perform the sorting here. Okay? So I'm going to show you how can we sort the data. I'm not going to talk about the in-memory algorithm that we are familiar with. No. I'm talking about the situation that what if the size of the relation cannot fit in the memory? How can I handle the situation? How can I sort this data? Then after that, we're going to talk about different algorithms allow me in order to perform the join of this relation. How can we implement the join algorithms? I'm not going to cover the rest because the main thing, if you understand how to do the sorting and you understand how can we implement, the joins or multiple algorithms to perform joins, and the rest is going to be, too simple. Similar to the join, actually easier than the join. Because maybe you're going to perform some sorting, you know how to do sorting, and you're going to see how can you use the sorting in order to implement the join algorithm, one of implementation or possible implementation. If you try to perform merging data, if you try to find the smallest value, the rest of the say, implement union, set, intersection, duplicate elimination, you need to sort your data, then you need to figure out how can you extract the information of the tuple and make sure the tuple does not exist in that, or this unique value. Or this is only the unique value of the tuple. So again, if you understand the join and sorting, then the rest is going to be too easy. And in the exam, I'm not going to ask you, for example, explain to me. We're going to mainly, I want from you to understand how this works, because if you understand how it works, it's going to be easy for you to estimate the discount on the output operation. So anyway, sorting. Why you need to sorting? Sorting is very important. Sorting allows me in order to perform, let's say, merge join, aggregation by sorting, and also I can use sorting in order to implement duplicate removal. This is one implementation. How to use the sorting in order to eliminate the duplicate of the data? You sort the data, then after that take the first tuple out and check. If you find any match, ignore, find the next tuple that doesn't match. So it's easy to perform the search if the data is sorted, right? So you can, because remember, if you sort the data, now we have one block, you are going to sort the data into blocks. You sort the data, then store the result in the disk, okay? When you read this one again, all the tuples are going to be next to each other, going to be in one block. So yeah, it's easy to read the data. Maybe you're gonna find the first tuple T1, and the rest is gonna be always equal T1. So you can say this is one, ignore the rest, jump to the next tuple. So I mean, it's one efficient way in order to implement the duplicate removal. Traditional sort algorithm like quick sort, etc., requires that the file must fit in the memory. If it's not, now we need to find a way. I'm going to introduce you to the two-pass multi-way merge sort, with the way that how, if you have a large file, how can you store the file on the disk, okay? Then after that, I'm going to show you that what if the two-pass multi-way merge sort doesn't work with my case. I need to go with the 3-pass and 4-pass and etc. So we can generalize the same pass. So suppose that we have in buffer, okay, available memory in the memory in order to sort the file, and the file cannot fit in the memory. This is the most important thing. How can you tell the BR is greater than, let's say, M? So in this case, yeah, by the way, one more thing here. When you say M buffer here, this means one page is equal one block. They are the same. So this means if you have 100 number of blocks that store the data, and you have 100 M of buffer available in the memory, they are the same. So again, one block or one buffer is equal to one block. They have the same size. Okay? So in this case, assume that you have M buffer. So the plan here to sort the whole relation, I'm gonna do what? I'm gonna take the M buffer in order sorting the data, okay? And in order to do that, I'm going to take the entire relation of the table here, divide this one into blocks and or chunks of data, and the size of each chunk is going to be M. Okay? Can you do this one? Yeah. So I'm going to read the first M blocks and put it to the, let's say, M buffer. Then, since this one is going to be in the memory, you can use any in-memory sorting algorithm. I'm going to sort them, then after that, store them back to the disk. Can I do that? Yeah. So here the block, we have, for example, M blocks, and can be sorted here in the disk. Then after that, perform the same operation for the second next M block. Fetch them to the main memory, sort them, then after that, store the sorted chunks to the disk. Continue this one until the file is done. And this is the first step. Take the file, divide it into blocks of M buffers, M blocks at a time. The last one is going to be at most M blocks they have. Yeah. Then after that, we assume that we have K chunks. Here we have a limitation of number of chunks, but we're going to talk about this one next step. Right now, we assume you have a K chunks. Each chunk is going to have like M blocks. So you read the first M buffer and the buffer, sort them. Then after that, store them back to the disk. So here, all the information in this block is going to be sorted. And here it's going to be sorted. Here it's going to be sorted. So you have a partially sorted. Okay, what's the cost of this operation? The cost of this operation, if the data is clustered, so it's going to be here, I need to have a BR in order to read the entire data, or blocks of the data, right? How many blocks? This input out operation depends on the number of blocks required to store this relation, right? I need to store the data to the disk, or to the disk. What is the cost to perform this operation? Is the BR. So the total is going to be 2 BR. So far, so good. Yeah? How is the data is unclustered? Oh, unclustered is different. Let's say unclustered. In order to read M blocks, how many disk out operation will you perform? It's more. It's not BR. It's not PM. It's not to say M times. Yeah? I'm going to perform more. It depends. Remember, in the clusters, every time we try to fetch one block, get tuples, I will fetch one block, end up we have only one tuple that belongs to this relation. So in order to fill, let's say, let me have this example here. Assume one block or one buffer, allow me to store 10 tuples. This assumption, okay? Of course, it depends on the size, but just in order to simplify the process. So if you wanted to fill one block or one buffer, how many disk input out operation you need to perform here? I need to perform 10 disk input out operation. For each of them, it's allow me in order to take or fill one tuple. So in order to have 10 tuples to be stored in one buffer, I need to perform 10 disk input out operation. So if the whole data is, for example, 1,000 tuples, in order to read the entire data, I need to perform 1000 disk and out operation. So in this case, the first step is gonna cost me TR, right? Because it is in the cluster. Then after that, when you sort my data, I'm gonna put the chunk some in M buffer. I'm gonna store the M buffer as one unit, as a chunk. So the data is gonna be in this step, no more unclustered. The data now is gonna be clustered. So I need to store BR here. So the cost here to be TR plus BR if the data is unclustered. If the data clustered, this means 2BR. Okay? Good. So why the number of chunks here we said is less than or equal M minus 1? This is constraint here. You can divide the data into blocks, M buffer, fetch M buffer at once or each time, sort them, and store the result in the disk. And we said the number of chunks cannot be exceed M minus 1. And I'm gonna show you why this is the reason. This is the limitation of the two-pass multi-way merge sort, which is the algorithm that I display. Okay, this constraint is imposed by phase 2. Okay, we're gonna see why here. How the phase 2 works, then after that, see why this is the constraint. The phase 2 is gonna say what? Now I need to do. Right now we have like a number of blocks, yeah? And the number of chunks here we said less than or equal M minus 1. I do have M buffer now. So I need to perform the second step. The second step is gonna say what? I want to sort this data somehow. I do have let's say K chunks, and the data within each chunk is sorted. But if the chunk 1 and chunk 2 is not sorted together, Okay. So what I'm gonna do? I'm gonna I do have M buffer, yeah? I'm gonna use M minus 1 buffer. And I'm going to associate one buffer with every single chunks. So that's why the size of the chunks must be less than or equal M minus 1. I do have one extra buffer, yeah, with the last one, because I use only M minus 1. I use the plus 1 buffer in order to what? In order to sort the data. So in this case, since I'm gonna associate one buffer with every single chunk, I'd use one extra buffer in order to hold the final result. So end up we have all the buffer here. Buffer is going to be M buffers, yeah? So I'm going to iterate to find what's the smallest value in the blocks that I fetch in the main memory. What's the smallest value here? Which is going to be fetched from this this chunk. One block from this chunk and one block from this. I'm going to fetch the first block, which contains the smallest value in per chunk. Now I can find out what's the smallest value among all of you guys. This one. Move this one to the buffer, the plus 1 buffer, the extra one, the output buffer. What's the second one? For example, this one. Move this one here. Not copy, move. Continue this one until this buffer is going to be full. If this one is going to be full, I'm going to store this one at the beginning here. So now this block is going to contain the sorted data for the entire data. Right? Do the next, continue this one. If this one is going to be full, store that buffer to the disk. Then after that, empty this buffer. And continue this operation. Assume that we have this buffer is going to be full. Done. So you have to fetch the next block. Done. Fetch the third block. Editor. You see that? This is the second phase. So that's why. So I need to have a limitation. Although this one works, we're supposed to have, M minus 1 at most chunks of the data. Because later I'm going to associate with each of them. We're going to assign one, let's say, buffer in order to read one block from each chunk, bare chunk. And the plus 1, or they say the last buffer here, or the output buffer, in order to hold the final result. Make sense, guys? So what's the cost of this storage? I'm gonna read the data again, okay? And I don't care about the final result for now. Unless, because remember, we talk about the different processing model, yeah? One of them say you will perform a join with R and S. Whatever the final result gonna be what? Whatever you produce here is gonna be fit to the higher level. So whatever operator the parents are gonna do with the data, it's not my business. Unless sometimes we're gonna say this is gonna be part of another operation, so we need to count the final writing. So right now I'm going to ignore the cost to write the final result. So whatever this buffer is gonna be blocked is gonna be fetched to or emit to the parent. Okay? And this is what we did here exactly here. Let's summarize what we did. We have chunks here, the second phase 2. We have assorted chunks. We have m buffers. I'm gonna allocate one buffer per chunk, and we have the one output buffer, the total buffer. So now m now in total, yeah. Once it's gonna be full, I'm gonna just want to store this one in the disk, or maybe I'm gonna send this one to the higher level, whoever wants the data or join algorithms. Okay. So as I mentioned, we're not gonna consider the cost of writing the output as a cost in order to execute this command or this algorithm. So this is an example. We have a set of attributes here. For example, we have whatever m blocks. Take the first one, sort, fetch the main memory, sort them. Now they are sorted. Take the next part, and etc. You see that at the end now. Once we're done, we do have each different chunks, and the size of each chunk is going to be m blocks, and the number must be less than or equal m minus 1 number of chunks here. And at the same time, the data is going to be partially sorted within each chunk of the data. Okay. Now with the second step, I'm going to have one buffer to read each chunk data, and I have one output buffer. The total is going to be m buffer here in total. Maximum. It depends, by the way. It depends on the chunks. Maybe you have a less m minus 1, but the maximum never exceeds m minus 1. So in this case, we can use, for example, try to fetch find the smallest data. How can I search? Your data is in main memory, so I can use whatever in memory algorithm in order to allow me in order to achieve this goal. Okay. Find the first, the second. Once it's going to be full, the store data in the disk. Now see AB. It's going to be the sorted data and continue this operation and so on. We said about the cost of this operation. So what's the maximum of the height file that can be used in this system? We have a formula. We're going to say if the BR this then equal m multiply m minus 1, then you can use 2 pass. Remember I said if the BR let's say greater than m, then you cannot use 1 pass. So you have to use 2 pass. 2 pass is going to have a specific criteria or requirement. If the number of tuple relations are less than or equal m multiply m minus 1, then you can use the 2 pass. If not, that means you have to use 3 pass or. So why this number? From where I got these numbers? Go back to the algorithm itself. That's why I said in order to estimate the cost, you need to understand how the algorithm is going to work. And also in order to understand the limitation, the constraint of high size constraint that in this whatever algorithm, you need to see or understand how the algorithm works in order to figure out how could you get this information. I'm the person that I hate memorizing stuff, so I don't memorize them. So I need just to understand them, so I will not forget them. And hopefully you too. Okay? So in the 2 pass here, remember, just I want to go back to one thing. We have m at most, by the way, m minus 1 buffers. Right? That's what we have here. In the phase 2. Okay? Those m minus 1 buffer, okay? Chunks of the data. What's the size of each chunk? We do have m minus 1, let's say, chunks of the data. And the size of each chunk is going to be equal to m, right? Because you have m chunks, m minus 1 chunks at most, and the size of each of them is going to be m. Why? Because this is m block. So we have m minus 1 multiplied by m, which is going to be what's the total number, what's going to be the size or total size of the file. Yeah, we can summarize it. We have pass 1, we have less than or equal m minus 1, and the one chunk is going to equal m block. So we can the PR, the file size less than m multiply m minus 1, or for simplicity you can say m squared. Because m is too large, so m multiply m minus 1 is going to be m squared, is going to be fine. Or in other words, we say if m is greater than or equal the square root of the PR, so in this case, yes, you can use this one. So that means you have enough memory buffer that allow you in order to store or in order to handle the file that contains this number of blocks. Okay? So the cost again. The cost of the relation, if we ignore the final result, is going to be 3 PR. I'm talking about the cluster relation. If the cost that must be included, say the final right, we don't have another operation. This is the only, we need just to solve the relation, then done. Or this, solve the relation, then after that done, then in this case you need to include the final cost. The final cost is the final writing operation. Okay? So it's going to be 4 PR. Good? What I'm like to do, I'm going to just show you that How can you compute the number of blocks here? Okay, yeah, the whiteboard is going to be easy. And there's a question definitely in the exam, simple, this one, how to compute that. Maybe in the quiz you're going to see that. So suppose that we have one block that's 64 kilobytes, okay? And the memory size available 1 giga. This is the whole memory, the entire memory that you have. You can use all of them. So I need to find out, for example, what's the number of buffers or the value of M that we have. How many blocks do we have? So you're going to take 1 giga with the whole memory, divide by the size of each block, or one block, all right? In order to give you how many buffers do you have. Here, we're going to use, to say, different notation. Either it's going to be binary notation or the decimal notation. I'm going to use the binary notation, okay? I know for the binary notation, you know that when you say, for example, 1 kilobyte, the decimal notation is going to say this one equal 1000 byte. For the binary notation, I know we use 1 KIB, which in this case 1024 bytes. Okay, so here I'm going to use the binary notation. If you answer this question using the decimal notation, it's fine for me. Either is fine. So the most important thing for me, the formula that we're going to use or how to apply the numbers. So in this case, we have 1 gigabyte. 1 gigabyte equal to what in the binary representation? 1 multiply 1024 multiply 1024 multiply 1024 divide by 64 multiply 1024. So this one with this one is going to be equal, let's say, 16,384 buffers. Give me how many buffers do we have for the value of M. Okay, I know what's the value of M right now, not 116,000. So what's the maximum file size that can be sorted? So in this case, you have a PR here. We know that's code, or the formula that we have must be M multiply M minus 1 in order to use this. Okay, blocks here. Right? Remember the constraint that we have? So in this case, I need just to plug the numbers. So I need what the maximum number of blocks here in general. If you want a size, we can compute the size. I'm going to compute the size too. So this one will be less than or equal. What's the value of M? 16,384 multiply 16,384 minus 1. This one is going to be blocks, right? This is the number of blocks that you have. So it's going to give you like a number 268,419,072 blocks. Do you want to, if you have a number of blocks, this is the result. If you want to know the exact size, I need to have a size of the file. So the only thing you need to do here, you take this number and you multiply, with what? Remember, we have this number of blocks. The size of each block is going to be 64 kilobytes. Multiply 64 kilobytes. So you end up, for example, in this case, it's going to be 17 terabytes. You see that? 17 terabytes can use two merge sort in order to sort this file. So here, based on the formula that we have, as I mentioned, you're going to show you many algorithms. Each algorithm going to show you, give you like, this algorithm can be used with this file that satisfies the following condition. The number of blocks, for example, less than or equal whatever, then you can, derive, the exact size of the file that you use, or you can use in order to perform this operation, or whether you can use this one or not. Okay? So when I can use this operation, so I give you different scenarios. Remember, this is sorting algorithms. So when we're going to use this algorithm? So it depends on operation that you perform. Sometimes you need just to say sort one relation. If you want to sort one relation, for example, in this case, sort is a relation R. So in this case, if the number of blocks are greater than or equal the available number of buffers, okay, then in this case, you can use the two-pass algorithm if the number of blocks are less than M multiply M minus 1 if you want to accurate. Why is I said this first condition? That means if the relation R cannot fit in the main memory, if it's fit in the main memory, please don't waste your time. Do the normal sort? Yeah, let's say, what if the relation R fit in the main memory? What's the cost of the sorting here? If the relation R, let's say less than M, for example, what is the cost of sort the relation R? So it's going to be TR, exactly. Why? Because I need to read the entire relation R. If the data is unclustered, If the data is a cluster, that means the total is going to be BR. Why? Because in order to access the data, it depends on the data. Yeah? If the data, let's assume the data is a cluster. Remember, a cluster doesn't mean the data is sorted. The only thing, when you fetch one block, you're going to find all the tuples that belongs to the same relation. So in order to sort this data, I need to fetch the data from the disk to the main memory. This is the only cost. That's why I said it's going to be BR if the data is clustered. If the data is unclustered, that means I need to perform, in order to fetch this data to the main memory, to the buffer somehow, I need to read the entire data. That cost me TR. Right? Then after that, nothing, done. I can use, let's say, binary sort or whatever, or merge sort, any in-memory algorithm to sort my data. So if the data can fit it, less than M, that means you can use one pass. Remember, one pass, that means you access the data one time. Either it can be BR if the data clustered, or TR if the data unclustered. In the binary operator, sometime later we're going to see one algorithm, we can sort two relations at the same time, if both of them cannot fit in the main memory. So R cannot fit in the main memory, and S cannot fit in the main memory. And also in this case, the condition, the number of blocks R plus S must be less than M multiply M minus 1 in order to sort both in algorithm together. Oh, sorry, both relations together. I'm going to talk about this one later, but keep in your mind, we can do that. There is one optimization, one join algorithms allow us, suggest to use this technique. If you have a multi-pass, multi-way merge sort, if it doesn't work too, you can use 3 pass, you can use 4 passes, you can use 5, etc. Okay, we have one thing we go over. I want to make sure that like one observation is going to help us in order to generalize this process. In this pass 2, in this case here, the only constraint that we have, the number of chunks must be less than or equal M minus 1. Did you say anything about the size of each sorted chunk? No. The size M minus 1, whatever, I don't care. The most important thing here, in order to perform the final pass or the next pass, the total number of chunks that we have must be less than or equal M minus 1 in order to perform the merge, okay, of the final, or they say, in order to perform the merge sort. Yeah, why is M less than or equal M minus 1? Because I need to have one extra, the one buffer here, used as an output buffer in this case. Okay. So there is no limitation about the size. The only thing, the limitation that we have here, how many buffers or chunks do we have here? Okay. If you give me a very large file, okay. In this case, just I want to find a way in order to generalize the 2-pass multi-way merge sort. Assume that we have a very large file. I'm going to take a look at the first M buffer, okay, and generate the say M minus 1 chunks. Or let's say, do this one for every single block. Take the first M buffers or M blocks, fetch them in memory, sort it, and store the result in the disk. Take the next M buffer, fetch them in memory, sort it. Take the third, and continue. And here there is a chance we do end up, we have the number of chunks, so sorted chunks is going to be greater than M minus 1. Right? There is a chance. If less than or equal M minus 1, then I can use 2 pass. If greater than M minus 1, so what I have to do in this case? In this case, though the number of chunks that we have is greater than M minus 1, I'm going to just focus and take the chunks of the M minus 1 chunks that we have, or sorted chunks, and the size I'm going to only treat M minus 1 at a time. So I can use the first M minus 1 chunks, sorted chunks, before like assign, let's say, or use one buffer to read the sorted chunks from these M minus 1 chunks, and use one output buffer in order to write the total sorted output for only those M minus 1 chunks. So we perform this operation, and I can have large M multiply M minus 1 block. Right? Can you do this one? Yes. Then after that, do the next. Take the next M minus 1 chunks. Perform the same operation. And continue, or compute to say the larger block size of the M minus 1, or so the sorted data. And continue with the third one. Continue with the fourth one. Continue with the fourth. So I'm continually using M buffer in order to perform this operation. So far, so good? Then assume that at the end, hopefully, we end up, we have, let's say, M minus 1 chunks at the end after perform this operation, then they can perform, let's say, then I'm going to do the final one. Assume that all the number of chunks that we have here, maybe it's going to be less than or equal M minus 1. Then in this case, I can use the final stage with the final step and repeat the same operation for the last time. I'm going to use n minus 1 buffer and the one buffer to read the sorted chunk, and I'm going to use the one output buffer in order to write the total sorted output. Then I'm done in this operation. If those number of tuple, I would say the chunks is not greater less than or equal n minus 1, continue doing this one with the first n minus 1 chunks and the next n minus chunks until you end up we have the final stage. The piece of final stage you're gonna have end up we have less than or equal or at most n minus 1 chunks. Then you can do the final stage. Yeah. So in the three pass multi-way sort algorithm, or merge sort algorithm in this case, the first one you're gonna divide the input, finding the chunks in blocks each, sort each chunk individually, then store the result in the disk. This is the cost going to be 2 BR, one reading the data and one writing the data, right? If the data is not a cluster, this means it's going to be 3R and number 2, and here it's going to be PR. This is the cost. Good? Now the next step. Assume they have more than n minus 1, so I cannot finish this one in 2 bus. So it looks like we have multiple bus. Repeat this operation multiple times. So it looks like if you take a look at the 2 bus multi-way merge sort, the second phase, in the 2 pass, I'm going to repeat this one as much as I need it until I end up we have the number of chunks is going to be less than or at most n minus 1 in order to perform the final step. One more time. For the second pass here, I'm going to merge only the groups of n minus 1 chunks at a time. That's what you build here. In order to have like, I call this one, let's say super chunk maybe, or larger. So the size of this one is going to be reduced n multiply n minus 1. Blocks do you have here? Because we have what? We have n minus 1 chunks, and the size of each of them is going to be m block. Okay? So this is the number of blocks going to be stored in this chunk, this super one. And continue doing the next one, and that's it. And assume that, so now what's the cost here? Regardless of the data is clustered or not, I'm going to 2 PR here. Because I'm going to read the data, and then we need to store the data. The sorting or storing the data here is going to be part of the result here. Yeah? This is going to be part of the competition. Assume that at the end, we have at most n minus 1 super, let's say, or much large sorted chunks. I'm going to perform the final result of the final phase, which is going to be rewritten one time, and I don't care. I'm not going to continue or to say, actually I care, but I'm not going to count the final output or store the final result going to be as a part of the result in this case. Okay? So what's the cost in this case? So it looks like in the phase 1, pass 1 or phase 1 is going to be PR, read the data, store the data. Then the second phase is going to be read the data and store the data again. Yeah? And the third phase is going to read the last file, the super n minus 1 chunks, which in this case, you have to read the data for the third time. And I'm not going to consider the final writing, which is going to be the sort when you perform this, use the last or one output buffer in order to merge the sort of the whatever n minus 1 sorted super chunks into one sorted output file. Okay? So the cost in this case, if you take a look, it's going to be 5 PR in this case. If the data is a cluster, GR plus 4 PR. We are not going to count the final output. If you're going to count the final output, it's going to be 6 PR in this case. So what's the maximum size of the data here? The maximum size that's going to be formed here is going to be n multiply n minus 1 square. Why? There's no memory restriction of the phase 1 and phase 2. You see that regardless whatever the data, I can use m blocks, repeatedly use the m blocks in order to, let's say, partially sort the data. Read the data m blocks, sort them, then store the result. I'm done. Right? Of course, m minus 1 and plus 1 as the output here. Perhaps the last one, we must have at most n minus 1 chunks in order to finish. It's going to be the final phase. Right? n minus 1, what's the chunks? We do have n minus 1 chunks. And the size of each chunk is going to be what? M multiply m minus 1. M minus 1 multiply m minus 1 here. Go back here. So what's the size of this chunk? M multiply m minus 1. How many chunks do we have? We're going to end up, we have m minus 1 chunks. I'm talking about the final step here. Yeah, actually here. We do have at most m minus 1 chunks, and the size of each chunk is going to be m multiply m minus 1. So we end up, we have m multiply m minus 1 square. Okay? This is the instruction here that we have. That means the maximum file size, the number of blocks of the file, BR, in order to use in this case, must be less than or equal m multiply m minus 1 square. So this means if BR cannot be used in the 1 bus, we cannot use 2 bus. Now try with the 3 bus. We cannot use this one with 3 bus. This means we can generalize this one 4 buses, 5 bus, 6 bus, and etc. Okay? This is just generalized, I mean, come up with a K-pass. If you can use 1 pass, 2 pass, 3 pass, etc. You can tell you what's the maximum or the cost in order to perform this operation and what's the maximum size. If you just substitute the K equal 3, then you end up, it's going to be work with the K. I mean, 3 pass. If you substitute K equal 2, that means it's going to be 2 pass. It's going to be have the right numbers for the 2 pass. Okay? And this is generalized, I mean, just come up with a general way or the general formula in order to compute what the cost of each, say, different algorithms. It depends, 1 pass, 2 pass, 3 pass, etc. And you're going to give you what the maximum size of each pass here. So what's the maximum size, for example, of the 2 pass here? You know that if you substitute the K equal 2, so then we have M multiply M minus 1, which is the number of blocks of the R must be less than or equal this one, yeah? If this 2 passes, 3 passes, that means if it be R, in this case, less than or equal M multiply M minus 1 square, so you can use this one. Of course, you have to check whether it can use 1 pass or not. If not, check with the 2 pass. If not, go with the 3 pass, etc. Good. Now I'm going to go over different algorithms that allow us in order to compute the join. How can we implement the join here? If we understand how to implement the join, that means the rest can be easy. The aggregation function, you're going to see, it depends on the sorting. We know how to use the sorting here. And you're going to use the hashing. I'm going to show you how to use hashing in the merge, in the joining here, algorithms. Selection, projection, etc. based on the index and perform scans. I'm going to show you that since we're going to use index join and we can perform the join using index, so we have an idea how can we perform this operation. So that's why the most important thing, if we understand the join and the sorting, then the rest of the operation is going to be easy. We are not going to cover all of them, just I'm going to go over different algorithms, the joins, which in there, and we need to compute the cost for each algorithm. Generally speaking, when you try to join 2 algorithms, okay, either going to, for example, 2 relations, it's a binary relation, by the way, operation, by the way. You have either going to say R join S or S join R. And here it must be natural join, theta join, either is fine, okay? The same structure again. Of course, you have minor modifications of the algorithm, but it's going to have the same structure. We can use the same algorithm that we covered here, okay? Here I give you some numbers, and here in this example, in order to join R with S, we have a different ways in order to perform it. Either going to be join R with S or S with R. The first one is going to be left-hand side operator or operand. It's going to use as in the outer loop, or it's going to have to use a special case or have a special treatment. That's why the one we put in the left-hand side, usually we prefer to be the one that has a smaller size. The relation has a smaller size. More detail is going to be a few slides when you talk about the actual implementation of every single algorithm. Okay? The other thing we can think about here, what kind of join algorithm we can use here? We do have, let's say, tuple-based algorithm. We have a block-based algorithm. We do have like merge join algorithm. We have index. We have the hash algorithm, a join algorithm, which we have a multiple way. So we need to just go over them, and each of them they have some advantage, disadvantage. At the same time, they have like a cost. The cost is going to be affected, going to help me how many available buffer do you have, value of M, and then you can decide which algorithm you're going to perform here, whether you have an index or not in order to perform this operation. So here we're going to use this example. Assume that we have 2 relations, and both of them are going to have a common attribute C. Okay, that's going to perform the join based on the common attribute C. Okay, and the number of tuples in the relation are 10,000. The number of tuples we assume here is 5,000 for the relation S. This is the tricky part. We said the size of relation R equal the size of relation S, whether it will be 1/10 of the blocks. This means one block can store 10 tuples from the relation R, and one block can store 10 tuples from the relation S. Here, for simplicity, we said the size of relation R and S are the same. In the exam, the quiz, they are not going to be the same. It's going to be different. So you need to here figure out, pay attention to this, assumption, or this, the information that they give it to you here. Again, here, when you say the size equal R equal to S equal 1/10 of the number of blocks, that means in this case we have a 10 tuples from relation R can be stored in one block. And 10 tuples from relation S can be stored in one block. Okay, or each block can contain 10 tuples. But in the exam or the quest, definitely each of them can have different parameters. Okay, different size. For example, one of them 15, that's one maybe 200 or whatever. The memory available is M with 101 blocks with the value of M. Okay, the metric that we need to cover or use here is only the number of disk input output operation that we need to perform. Okay, so as I mentioned, we are going to ignore everything. The only cost that we need to compare the number of disk input output operation. As I mentioned, we do have a different ways in order to, let's say, compute the join, change the order, whether it's going to be R join S or S join R. We have different join algorithms, iteration, merge, join with index, and hash join. And we do have many factors that affect the performance. First, we need to tuples of relations stored, maybe they'll be physically together or not. Whether this is going to be clustered or not. This is the meaning here. When you fetch one disk without operation, how many tuples that belong to this relation that can be exist there? If the data is unclustered, that means when you fetch one disk, perform one disk out of operation, you're going to find only one tuple that belongs to that relation. Okay? If it's clustered, that means all the tuples that's stored in this block is going to be belongs to that relation. Whether the relation is going to be sorted or not. That's with some algorithm, you're going to see that require the data must be sorted based on those common attributes or sort the joint attributes. If it's going to be sorted, it's going to be perfect in this case. You see that? They're all the whether there's an index or not. So I'm going to show you the simple thing, the nested loop join, which we call this one 1.5 pass. Algorithm, weird name. 1.5 pass, that means one relation, we're going to scan this one, only X this one time. And the other relation, we're going to be X that relation multiple times. That's the meaning 1.5 pass. Okay? So it looks like we have iterated loop. Okay? We don't, it's not required that one relation can fit in the main memory. So here, this is the simple algorithm. I do have 101. Remember, this is the given information. This is the tuple that the buffer that we have. You can perform the tuple-based nested loop. I'm going to say here, in this case, R join C, for example, S. The one in the left upper hand, the one is going to be in the outer loop. And the one here is going to be in the inner loop. Okay? So here, you're going to have one block for the relation R, this relation R here, and the relation S. Okay? You have one block, you have to read this relation R, and this, for example, the entire relation S. You can divide this one, it depends whatever blocks are going to be stored. Read one block to the main memory. I'm going to use only one buffer to the relation R and one buffer to the relation S. So in this case, we still have 99 buffer available. We are not going to use them. So here only two input buffers. Read one block from the relation R. For every single tuple for this tuple, of course you need to iterate every single tuple in this block. You need to read the entire relation S. That's the meaning here. In order to find the match. Since we do have only one block, one buffer we use for the relation S, so for the relation S, I'm going to read one block at a time. Then here for every single tuple for relation R, I need to find a match for every single tuple in this block here for the relation S. When it's done from this tuple or this block, I'm going to fetch the next block from the relation S to that buffer. And still we have a iterate for every single tuple here for every single, say, tuple in the relation S. So in other words, when I'm going to read one tuple from the relation R, belongs to the R, then I need to scan the entire relation S to find the match. I need to perform this operation based on the number of tuples of the relation R. This is the process that we're going to perform. You need to understand the structure, how the algorithm works, because you need to compute the, let's say, or estimate the cost. Okay? So we're going to back to the numbers that we have. And in this case, assume that R is the outer relation. Based on the algorithm, for every single tuple of relation R, you need to scan the entire relation S to see whether they have, of course, you need to find the match. If the R.C equal S.C, then in this case, you're going to output, concatenate them and output as a result. So for every single tuple of relation R, this is the cost. I need to read the tuple of relation R. Then I need to read the entire relation S. So what's the cost? The data is not clustered. So in order to read one tuple of relation R, you are going to perform one disk input out operation, right? One. That's why I said one. In order to read the entire relation S, of course you have to read this one as one in the block. Okay, in base. Okay? In order to read the entire thing, how many disk input out operation in order to read the entire relation S? Can you use a BR here? No, because the data is not clustered. For every single disk input out operation, I will be managed only to retrieve one tuple that belongs to the relation S. In order to read the entire relation S, that means you need to read or perform the TR here. Sorry, TS. So TS in this case, since you have 5,000, so this is the cost in order to, just for every, or for one single tuple for relation S. For the relation R, sorry. And in order to compute the total cost, or input out operation cost, since we have TR tuples, I need to multiply this one, multiply by the TR here, which will be 10,000 multiply the whole operation here. Right? You see that the number is too large. So this is a bad way to perform that, use iterated loops. In other words, when you use a Cartesian product, this is the simple way to implement the Cartesian product. Iterate every single one tuple of relation R, then after that you need to iterate over every single possible relation S, then you need to perform what? Do the matching here, which is a bad idea to perform that. Make sense? The data is not clustered. If the data clustered, these things can be changed, it can be less time. Okay, I'm going to give you an example in a few slides. Someone has said, okay, now we do have 100 buffer that given, the value of M. You use only 2 of them. Why we cannot use the rest? Now we're going to talk about something different. It's called the block-based nested loop. This is the algorithm, looks like something like this. You are going to join S with R. And also you can do this one in the previous step, okay, or the previous algorithm. We prefer to use, the left-hand side, or the one that's going to be the left operand. Operand is going to be the relation that has smaller size. Okay? The smallest relation then from between R and S. Why? Because it's going to have better performance, a little bit. Compared if you use the large relation, it's going to be as the first operand, or the left operand. Whatever you have the left operand, going to be in the outer loop. That's the meaning here. Okay, so in this case, I do have M minus M buffers. I'm going to use M minus 1 buffer in order to read the data from the outer loop. In this case, for each M minus 1 block of S, you have to read or fill M minus 1 block or buffer in the main memory. You have to read the data or number of blocks. It depends. If the data are clustered, that means we have to perform M minus 1 disk input out operation in order to read the blocks from the disk and put this one in the M minus 1 blocks or buffer in the main memory. All right. If the data is not clustered, now it's complicated. I need to find, number of tuples in this relation S. Yeah, it depends because I need to perform more or many disk input out operation in order to fill M minus 1 blocks in the or buffer in the main memory. This example we're gonna go over this one later. Anyway, you take chunks of the data M minus 1 at a time for the relation S. Then in this case, you are going to organize this one using, let's say, any social structure. You can use hash table, you can use binary search tree, whatever. The way that is going to help you in order to search within these M-1 blocks, to simplify the process. So the data in the main memory, we don't have 1 block, we have M-1 block of the data. Then now we do still have 1 extra block, right? Because we have M buffers. We use only 100 for the relation S, and now we're going to use the 1 of the leftover block in order to read 1 block from the relation R, 1 block at a time. Then in this case, for every single tuple that's stored in this one, in this block that belongs to the relation R, I need to search using whatever search structure that I built using the M-1 in order to locate which block the tuple that set of tuples that satisfy this condition they have, whatever. If a hash table or maybe you have a binary search, you can search for the value that they have the common attribute based on the value of C between the R and S. Okay? Then after that, you output the result. And you continue doing this operation again and again. You take the next M-1 blocks of the data. Okay? See this one with the example here. GR the TS. And we have the same number, 1 block that contains 10 tuples belonging to the relation R or the relation S. We still have one number of blocks here. Now I'm going to put R as the outer loop. And the next slide, I'm going to use the smallest relation going to be as the outer loop. Okay, so what does that mean? An outer loop, that means based on the algorithm, I'm going to use what? I use M-1 block for the relation R. So assume this is relation R here. This is the data we have 10,000. Now we need to have, let's say, M is equal to what here? 100. It's 101, yeah? This is M-1. I need, for example, 100 blocks here. So I need to fill them with data from relation R. If the data is not contiguous, it's not clustered, that means for every single disk input out operation, I can manage to have, let's say, only 1 tuple, all right? 1 IO is going to fill only 1 tuple in M, and 1 block in the main memory. in the buffer. So in order to fill one block here, assume this is block 1, this is block 100. In order to fill this block, how many disk input out operation I need to perform here? In order to fill only one block here, or one page from the relation R. One disk input out operation allow me only to store only one tuple. I need to fill this block with tuples. How many disk input out operation I need to perform? One, allow me only to have one tuple. And the size, based on the size here, tell me that in order to fill one block, you need to perform exactly 10 disk input out operation, because you need to perform or fill this one with 10 tuples. So for each one, it's going to perform 10 disk input out operation, right? In order to fill n-1 blocks, or let's say 100, how many disk input out operation I need to perform? It's going to be 1000. Right? So this one, I need to perform 1000 disk input out operation. In order to read data from here, it's going to be actually 1000, and store this one into 100 blocks or page in the main memory. Makes sense? If you understand this one, then you don't have a problem with the rest of the class. Of course, you need just to know the rest of the algorithm. This is the confusing part. Okay? How about S? Now for S, I need to read for the relation S. We have a data, 5000. And I need to fill one block because I use n-1 for the R and 1 for S. I need to fill this block with data from S. How many disk input out operation I need to perform here in order to fill one block with data from S? And both of them are not contiguous, not cluster. One disk input out operation allows me only to have only one tuple from the relation S. In order to fill this block, it depends on the size, it's going to be again, it's going to be 10. Right? That's what you can perform here in order to just to fill this with data. I need to do this one for right now. The system is set here. Let's see, to clear this one. If you take a look at the algorithm is set, you're gonna fill the data or use n-1 chunks from the relation R. Then after that, use one block in order to read the entire relation S. One block at a time. Yeah, in order to perform the operation. So here, the relation R is outer relation. We do have 100 buffers because the value of M is set 101. So I need to use m-1 for the relation R to fill with data. So I need to use 100 buffer. And one buffer for the relation S. So the total would be 101. The cost of each R chunk, so you need to m-1 chunks of the data from the relation R. It's going to be 1000. And you know why. You know, we do have 100 blocks, and each block can fit 10 tuples from the relation R based on the data that we have. Then in this case, I need to perform 10 input out operation per tuple, per block, multiply by 100, so end up we have 1000 input out operation. And for the relation S, since I need to have one buffer, one block, I need to read the entire relation S. Since the data is not clustered, so in this case, I need to perform 5000 input out operation in order to read the entire relation S. Of course, it's going to be used as one block at the time, or to say 10 tuples at the time in order to perform this operation. So m-1 can be fixed, and you need to read the entire relation S. What's the cost of this chunk? It's going to be what? It's going to be the cost of reading m-1 to be 1000 plus the cost to read the entire relation S, which will be 5000. So the total will be 6000 input out operation. This is only for one chunk. How many chunks do you have in the relation R? In other words, now you take the rest for the first n-1 chunk, you fill this one with the data. Or in our example, the first 100 buffer. Now you need to fill the next 100 buffer with the next of the rest of the data of the relation R. So you're going to perform every time or every chunk of the data, you're going to be able to read 1000 tuples of the relation R. Since you have 10,000, then you're going to perform this operation how many times? It's going to be 10,000 divided by 1000, going to be perform this operation 10 times. Again, in this case, if the relation R, this is the relation R, I'm going to read the first, fill the m-1 chunks. Then after that, I need to fill or read the next m-1 chunks. And continue this one until read the entire relation R. Yeah. For every chunks, I'm going to perform 1000 input out operation, which allow me in order to read 1000 tuples. Since we have 10,000 tuples, yeah, and each chunk will be 1000, so we end up we have 10 chunks. So we're going to perform this one 10 times. Each of them, you're going to read what? You're going to read the entire relation S. So it will be 10 multiply the cost for reading each chunk, 1000, plus the cost to read the entire relation S, which is going to be 6,000 multiplied 10. We end up, we have 60,000. You see that? If we compare this one with the previous algorithm, this is more efficient. It's at least we don't have 50 million. Now, what if we reverse the join order for the relation S and R? I put S at the small relation, so it will be the outer loop. The one's going to take m minus 1 chunks. You need, by the way, to understand, this is, the second algorithm. I'm talking about the block-based. I'm not talking about the iterator, let's say, the tuple-based. Tuple-based, one tuple, one block, one block. Block-based, there's means in this algorithm, m minus 1 chunks of the outer loop at a time, and you have to read the entire, let's say, relation. For the inner relation, you have to read the entire inner relation. And you need to continue to perform this one multiple times, depends on the chunks that you have. This is the same structure. I'm going to, since the data, both of them going to be on a cluster. Okay? And remember, the size of relation R, the tuple relation R, equal the size of relation, tuple relation S. And that means in this case, one block can contain 10 tuples relation R or 10 tuples relation S. If the size is different, that means the number is going to be different, not be the same one. But here, since they are the same one, maybe it's going to be confused here. Because I'm going to say, I'm going to assign, say, m minus 1 to the relation S, which in this case 100 buffer, and 1 to the relation R. I need to read the chunks of m minus 1 to the relation S. Now I need to check how many block tuples can be stored in one block in this case. It might be different number. Here, since they are the same, that means 10, both cases. So this means in order to fill 100 blocks, since the data are in the cluster, that means I need to perform 1,000 discount auto operation. Okay, the cost to read m minus 1 chunks of the relation S, 1,000, plus the cost to read the relation R, since it's not clustered, it will be 10,000. Okay, so the cost in this case 100 is 11,000. Okay, now how many chunks I need to, how many times I need to perform this operation? I need to read m minus 1 chunks of the relation R, S, one at a time. How many chunks in total? Since you have 5,000, this is the total number of tuples that you have, and in order to read the cost, in order to read the number of tuples is going to be read per chunks is going to be 1,000. So in this case, it's going to be 5 times. I need to perform this one 5 times. So it looks like we have 5,000, and each 1,000 is going to be one chunk. So this means makes sense. We have 5. So you multiply this one with 5. It's going to be the number to multiply by 5. So the total will be 55,000. It's slightly, better, slight advantage using the smaller relation in the outer loop. Okay? But remember, in this case, we assume that both of them have the same size. This is what's called, the block base. We still keeping saying, can we do better? Yes, we're going to keep doing this one until we cover the rest of the algorithm, the joint algorithm that we have here. Okay? What if? Assume the data is going to be clustered. Oh, clustered is perfect. If the data is going to be clustered, the number is going to be goes down dramatically. You're going to see that. Assume that the data is going to be clustered. If the data is a cluster, this is a big question to you guys here. Where's the BR, the BS here in this case? If the data is clustered, how many blocks do you need to store the relation R here? Or how many blocks do you need to store the relation S here? The relation R, the number of tuples of the relation R is 10,000. And the number of tuples of the relation S is 5,000. Okay? And the size of R equal the size of S equal 1/10 of the size of the block. Each block can contain 10 tuples. So the R is going to be 1,000 and S is going to be 500. Because remember, we assume that every block can contain 10 tuples for the relation R or 10 tuples for the relation S. So we have 10,000 and the block can get only 10 tuples at a time. It can be stored in one block. Then we divide them, you can end up, you have the number of blocks that you have that are required in order to store this relation. Based on this number, if the data is a cluster, by the way, both of them, okay, sometimes maybe we're going to trick you, give you one of them a cluster, the other one is unclustered. So you need to pay attention. As I mentioned, the exam is going to be, by the way, it's too easy. The only thing you need just to pay attention to the problem. Sometimes clustered and unclustered, maybe both of them unclustered, maybe one of them clustered, the other one unclustered, and the size maybe is going to be different. You're going to use the same structure. The only difference is just pay attention to the numbers. Okay? So in this case, assume that data is going to be less clustered. So I'm going to use S, is going to be outer loop. Remember, we have m minus 1 for the S, which is 100, and 1 for the R. Okay? in order to fill 100 blocks, or the buffer in the main memory, or read 100 blocks, or fill 100 buffer in the main memory from M, from S, how many disk input out operation? For every single disk input out operation from S, I'm being able to fill one block because the data is a cluster. Yeah. So in this case, the cost in order to just to read or fill, let's say n-1 or fill n-1 buffer in the main memory from the relation R, it's gonna be 100. Again, every single disk input out operation allow me in order to store or fill one block in the main memory. So since we have 100 blocks, I need just to perform 100 disk out operation. Again, because the data is a cluster. This one 100, okay? Plus the cost in order to read the relation R. Is R clustered? Yes. That means in this case we to be R here in this case. So in this case we have 1000. If the relation R is not clustered, it's going to be 10,000. Multiply how many chunks do you have here? We have 500. And for each time we're going to manage to read 100 block at a time. So in this case, we end up we have 5 chunks. If you multiply these numbers, you see the number is going to be 5,500 input out. Instead you have 55,000 input output. Now we end up we have 5,500. You see that right now, the way that you're going to store the data when you're keeping saying in the first day, we need to reduce the number of disk out operation. We need to keep the data contiguous next to each other, so in order to come back to one block together, in order to achieve this a better performance later when you try to perform an operation. And this is, an example. You see that it works fine with us. The other algorithm is called two-pass algorithm based on sorting. I'm going to show or talk about the sort merge join. Which this means in this case, the data, in order to perform the join, you have to sort the data first. Then after that, you're going to join them. How can you sort the data? I show you that an algorithm is called two-pass multi-way merge sort algorithm, and you can generalize this one to the 3-pass, 4-pass. This means here in this case we have to use 2-pass. It depends. It depends on this. You know that for every single algorithm or this algorithm, we do have many forms. Yeah, each of them they have some requirement. For example, take a look at the relation R. You need to sort them in order to perform this operation. In order to sort the relation R, what if the relation R can fit in the main memory? Then in this case, do we need to perform two-way merge sort, or 2-pass, or 3-pass, or 3? No, I can use only 1-pass. So the cost can be only to PR if the data is clustered, or TR if the data is not clustered, right? Can you sort them using 2-pass? Yes. No, 3-pass, and etc. Okay? So that's being is here only 2-pass. Anyway, so the sort merge join algorithm requires the data must be sorted. If the data is sorted, then here we're gonna ignore the cost of the sort algorithm, and now we need only to focus on the cost of the merge. In the sort merge algorithm, you need to combine everything: the sort of the costing plus the sort of the merging. And here, remember when we talk about the sorting, we said the final result, there is no need in order to count it in the final. We need to compute, the cost of this operation. Here, yes, you have to compute, add this one to the cost of this operation here. Why? Because in this case, when you sort the data, I'm going to sort in the disk. Then after that, I'm going to read it again in order to perform the merge. Later, I'm going to show you that some optimization, how can we make it better. Okay? So anyway, I give you two relations, R join S, or S join R, whatever, based on the condition. And I said that I'm going to use the sort merge join algorithm. So the sort merge, you need to check whether R and S are sorted or not. If they are not sorted, you have to sort them and keep the cost of sorting here. So in our case, if you take a look at the relation R and S, it looks like it satisfies the condition that we can use two-pass algorithm. Yeah, you can perform this operation in order to sort them here. Why? If you take a look at the number of blocks of relation R, it's going to be, let's say, greater than or equal the available buffer. The buffer is going to be 101. The number of blocks of the relation R is, if you remember, 1000. Remember? Yeah, so it's greater than or equal. Yes. And also, we can use the two-pass algorithm if the number of blocks of relation R is less than or equal m multiply m minus 1. Or m squared in this case. Yeah. When the number of blocks of relation R is 1000, definitely less than or equal 101 to the power 2. Right? So I can use them. This is the condition that you have to perform. You have to make sure that you can use. If not, that means go to the 3 pass, or maybe 4 pass, or 4 pass, and etc. And for the relation S, it's going to be the same form. So we can sort the relation R, then sort the disk, and sort the relation S. After I sort the relation R and the relation S, now I'm going to perform now a join of the sorted relation. Now we do have relation R sorted, and the relation S is going to be sorted here. So in order to perform this operation, we do have a buffer. We can use them again. The number, for example, in our example 101, just an example. So I'm going to use one buffer for per relation, okay? And we assume that the small, or let's say the small join value may, let's say, occupy less than one buffer. In other words, if you sort the data based on the value of C and the relation R with S, for each block, it's going to be all going to have the same value. In other words, cannot span to another block. If that could be spanned to another block, that means we need to have more than one block in order to read all the smallest value of the value of the C that have the same value here. Okay? So here, assume that one buffer is enough in order to really say, in order to have all the value of C with the same value. So I read one block here in this buffer, one block here in that buffer. Then I'm going to do what? I'm going to find matching between of them. This is the smallest value here, and this is the smallest value for relation R. This is the smallest value for relation S. If the smallest value required from you to have another buffer, so maybe you can use another buffer here, because you still have 99 extra or available buffer here. Okay? Then this is the smallest value here, can fit in 2 blocks, for example, and for relation R can fit only 1 block, for example. Okay? Then now find the smallest value here, compare with this value, and see whether they're equal or not. If they're equal, then you can perform matching. If not, then you're going to jump to the next one. Of course, the way that you perform the match is not simple like this. I'm going to show you the example. How can you perform this one? But this is like a high-level abstraction. How can you perform the join using the sort join merge? So this is sort merge algorithm. Looks like something like this. Take a look at the relation R and S. If they are not sorted, sort them. Done. Next step. Now I need to perform something interesting here. It's not interesting. I'm just sometimes excited. So anyway, if you have the relation R here, let's have an example here. Yeah, good. Then after that, go back to the slide. In order to perform this join here, you have, for example, 20, 20, and you have a 20, 20. Here the relation R and the relation S. In order to find now the smallest value, this one block here, and this another block, right? Now I find they have the same value here. The smallest value of R has the same value for relation S, with this relation S, right? How can you perform the join? This is the join you can perform. You join this with this element, and also this with the next element from the relation S. Then after that, you need to perform the following. Next value from the first value, this tuple with this tuple, and this tuple with this tuple, right? This operation. How can you perform this operation here? So that's why we have 2 algorithms. One algorithm just in order to specify, find whether the value of R, a value of C at this tuple from the relation R is equal to the value of C and the relation S. If they are, this means go to another algorithm in order to take care of the way that you need to merge all the possible combination between these tuples. Because might have multiple values. You need to perform something like this. And also the outer algorithm or the other algorithm going to make sure that, for example, if I'm here, the value of S here, or C at I or R here, and the value of C at the relation S or tuple S in that block is equal to 5. If the value of R is greater, C greater than the value of S. So in this case, what I need to perform here? That means in this case, I either maybe finish sorting this element or matching with or joining this tuples. So I need to advance to take the next tuple of the relation S. If the value of here, in this case, for example, is less than the value of S. So in this case, what does that mean? That means if this value is less than, this means you need to advance, go to the next tuple of the relation R. Because you have done working or processing this element. Okay? So back to the algorithm now, here. So in this case, the first I need to sort them if they are not sorted, done. Then the second one, now we need to iterate this operation. I need to find I'm going to use 2 pointers, I and J. I is going to be pointing with the current position in the relation R, and J is going to be pointing to the current position with current tuple in the relation S. The value at this position, I and J, as long as we still have tuple relation R and S, we need to perform this operation with the while. Okay? If the value of I dot C is equal to the value of J dot C, the pointer I, J, and R and S, they have the same value. That means please go there and output tuples, because you need to find out, maybe you have a multiple value, so you need to perform something. For every single tuple relation R, you need to join this one with every single tuple relation S. Well, they have the same value, I mean. Maybe you have more than value, one tuple relation R, they are equal to one tuple relation S, one tuple, so you have to perform this operation. Again, every single tuple relation R must join with every single tuple relation S, which is going to take care of this part. Else, they are not equal. If the tuple of the current value of C at I is greater than the current value of C at J. What does that mean in this case? For example, this is 10 and this is 5. Oh, in this case, that means I'm done from the J. I need to jump to the next tuple of the J. That means advance to the next value of that tuple J for the value C. If the opposite, that means I'm done from the relation R. I need to jump to the next tuple or the next value. Actually, not the next tuple. I'm going to say the next value of J, I mean, in order to perform the operation. Right? So let's take a look at this. How can you output tuples? This is just an example, okay? This pseudo code just how it works. You can maybe have a better idea if you try to implement this one. So in this case, remember, we have one point of relation R here and J, and we need to find all the combination between them here. So with J plus 1, with J plus 2, for example, this I. Then after that, I need to perform this case here. I plus 1, this have a different color. Assume they have the same value. I plus 1 is going to be with the J plus 1, with the J plus 2. Something like this. So in this case, I'm going to use, as long as the values, they are equal, the value of I and J, they are equal. That means you can perform this operation. And here I'm going to use, instead use J1, J2, J3, then after that I'm going to use the value of J. I'm going to use a K as a pointer in order to hold the current value of J. Because in every single iteration, in the inner loop, I need to iterate with the value of J from the beginning. Because I need to take the next tuple of the relation R, and you need to join this one with the first tuple, with the second tuple, with the third tuple of the relation S. So in this case, I use J. I mean, keep the value of J into the K. Then while the value of R C equal the value of K to C, since this value equal this value here, then you can join them. And advance the value of K equal to 1. So instead of using J, I'm going to use a K plus 1 and K plus 2. Yeah? So you can jump to the next, as long as they're equal. Then after that, once I finish this part, I'm going to advance the value of I. Say I now go to the next tuple. Check if they are equal to the value for J or not. Still we have a tuples, the K, put K, J of the K, and make sure this one is going to start in the beginning and make sure they have the same value, and continue advancing this one operation. Here we end up the value of I there has a value, is not equal to the value of J, then it can exit this loop. Okay? So that's how it looks like in relation R and S. You need to solve them. After that, you can compute this cost here in the whole operation. Assume that both the relation R and S are sorted. The relation are contiguous, or let's say clustered. So do you have any cost associated with the sort? No. The cost of the sort is 0. Plus I need just in order to perform the cost in order to perform the join merging here. What's the cost of the merging here? You're going to read the entire relation R one time and the entire relation S one time. All right? If the data are clustered, both of them are clustered. So in this case, the cost of reading the relation R and S, it can be the number of the number of blocks required to read the entire relation R one time, and I'm going to read the relation S one time. If the data is not clustered, so in this case, what's the cost here? It's a tricky question, by the way. If the data is not clustered here, so since the data can be sorted, once you sort your data, so in this case, the data can be is clustered. Because when you sort the data, you're going to combine all of them next to each other, right? Then in this case, it's going to be a BR, the PS2, plus the cost of sort the relation, if the data is not sorted. Anyway, so the total cost here in general, assume that we're going to use sorting, and the data is not sorting. So the cost of the sorting is going to be 4 BR. I'm going to include the final writing as a cost of this relation. Because I'm going to sort them, then I've sorted it in the disk. Then after that, I'm going to read this one again and perform the next operation, which is going to be starting doing the merging with the other relation. So in this case, it's going to be 4 BR in this case. Okay? What if one of these relations is going to be too big? Sometimes, maybe, usually when you say S, Sometimes, most of the case, the relation S is the one has a small size relation compared to the R. Sometimes S maybe can't use 2-pass multi-way merge sort in order to perform this operation. Relation R maybe can use 4 or 5 passes, it depends. So each of them has its own cost in this case for the sorting. Right? But when you perform the merging, just you need the number of blocks in relation R plus the number of blocks in relation S. And done in this case. Okay? Let's have a number here. I'll go with the numbers. The data are not sorted, but contiguous, clustered. Okay, in order to perform the sort cost here, each tuple is going to be read one time, written. Yeah, the final writing must be part of the cost here. So in this case, in order to sort the relation R, I'm going to, since the contiguous, it's going to be for BR for the sort relation R and for BR for the relation S, because both of them can use, 2-pass multi-way merge sort. Okay? The total cost in this case, the sort cost plus, the join. What's the join? PR plus PS. So it looks like you have 5 PR plus 5 PS. Right? Someone did you notice something that we have something weird here? If you go up here, just one, the cost is 7,500. If you compare this one with the block nested loop, a block algorithm that we talk about, this one was going to be 5,500. So it looks like that one is going to outperform, let's say, the nested loop join. They talk about this one. It's going to outperform, let's say, the sort join. Not exactly. Remember, the size is too small. For the small size or small, let's say, relations, it might be the case. But for the large amount of the relation that have too large, in this case, you're going to see that the merge sort or the sort merge is going to be outperforms, the nested loop. Take a look at the numbers here. Assume that we have 1,000 blocks in the relation R and 5,000 blocks for the relation S, with the number PR, the PS here, actually in this case. And both the data can be clustered. Okay? In order to perform this operation, and the data, they are not sorted, both of them. Remember, for the block nested loop, you're going to use what? You have n-1 chunks of the data. You divide the data, n-1 chunks. For each chunk, you have to use the entire relation, the inner loop, right? And you have to perform this one number of chunks. This is one way in order to compute the number of chunks that we have in this relation. So you can use the PS divided by M, the number of value of M, both since the data is going to be like, in this case, just going to be like clustered, so we can use this formula. Multiply with the cost of reading 100 blocks with the base value of M, plus to say the cost in order to read the entire relation R. Sorry, in this case, I'm going to use the PR since the data is going to be clustered. This end up, we have 505,000. Okay? Almost 5 million input out operation. If you perform this one using the merge join, maybe we're going to have 5 BR plus PS. Yeah? The cost of the sort, then after that, the merge. You end up, we have 5 multiply 10,000 plus 5,000, we end up, we have 55,000, and this one is going to be almost 500,000. You see that? So in this case, if a large amount changes the whole scenario, we have a large amount of data, then the sort merge join is going to be outperform the nested loop in this case. Okay? That's what you call about the 2-pass before. Just to remind you, this is, condition constraint in order to use M-pass. 2-pass. Yeah. And also, we assume the data, the R and S, neither of them can fit in the main memory. If one of them fits in the main memory, this means the cost of the sort PS, for example, in this case, is going to be only PR. Okay, if the data clustered, and TR if the data is going to be clustered. Actually, it can be 2 PR. Yeah, let's do this one. Assume the data PR or the R, this can fit in the memory. In M. So what's the cost of sort S in this case? So in this case, if the data, say 1 is unclustered, 2 if they are clustered. So if unclustered, that means you're going to perform what first? TR, read the entire relation S. Then after that, we have to sort this one into the disk later, PR, right? If the data is clustered, it's going to 2 PR. S, I don't know why I say R, it's S. The only thing that we need to perform, just how can we put all the stuff together, okay? One thing we can perform here, we got to talk about an advanced sort merge join. This is like a simplified version. You can sort R and S together at the same time. Remember, we talked about in one of the previous slides, we talked about two-pass algorithm. We said that we can use binary operator. In this case, we said in order to merge or say sort R and S at the same time, you need to have the PR plus PS less than or equal M squared. So in this case, we perform what? Instead, what we're doing actually in the sorting, then after that, doing the merging. Also perform, let's say, merge join. You take relation R. Let's do this one here. Relation R. Divide this one into chunks of M minus 1, M blocks. Sort this one local here. Then after that, store the disk. So here we end up, we have M minus 1 chunks at most. Yeah, this is the total. Then after that, we're going to use this one here in order to sort them. All right? This is the sorting. Then after that, we take a start here. This is the sorting. You have to read the data again. Then you do have like what here? We have one block here in order to find, for example, read the relation R here. Then we're going to perform the same operation with the relation S. Sort them, chunks. Then after that, one block per chunks, you M minus 1, then one output, and put the result in the disk. Then after that, you take this one in the disk here. And the second, now is still doing the merging. Read the relation R, read the relation S, one block at a time. You can use only one block in this case. Assume that the smallest value can fit in one block, one buffer. Then after that, you perform what here? You do this one to say merge them. And the result, we don't care. This result is going to be passed to the final, or let's say to the next step. That's what we're doing. One thing someone will say, okay, what are you doing here? It looks like you read the data here, in this state, phase 2 here. Then after that, sort to the disk. Then after that, you're going to read the data again here. How about if we mix the second phase with the merging phase? So instead here, we try to find the smallest value between of them. Then after that, sorted. How about that? We combine this step here and this step here. And now in this time, we are going to do the merging, or the join merge. That's what we're doing here. If we do have enough space of M that allow me to sort R and S at the same time. Before this one, we usually do this one in separate steps. We sort the relation R, store the result in the disk. Then after that, you use the M buffer in order to sort the relation S, store this one in the disk. Then after that, we're going to use M buffer in order to use blocks with the relation R and S in order to perform the merge join. All right? Here, if we have enough space, if the value of M, here in other words, greater than, let's say the PR plus the PS is what? Can be, let's say, less than or equal M multiply M minus 1 or M squared. Then in this case, I do have enough buffer of M, allow me in order to sort the relation R and S at the same time. So we can do this step here. I'm right now here in this step and here this step. We do have enough M buffers. Okay? So of course, this will be divided by 2, because now we're going to say divide M minus 1 is going to be this side, and M minus 1 will be this side. So it's going to be divided by 2 in order to have, let's say, total number of buffers going to be M. Okay? So in this case, instead we have doing sort them, then after that sort the disk, then after that read them again in order to try to find the margin or just join them, try to check the join algorithm or value with the match, then after that we're going to join them. I'm going to read this one in the M, or say assume M divided by 2, for example, buffers, and I'm going to read this one here. Then now, this step, I'm going to use the plus 1 here to find the smallest value. Then after that, doing the merging here. So here, instead we have the smallest value, I'm going to do the merging and store the result, or send the result to the next level. So the cost in this case, one time to read the data, one time to write the data. If you use 2-pass multi-way merge sort, then after that, the third time I need to read the data, and the final result is going to be the sorted data. Clear, guys? That's what is called the advanced sort merge join, which instead of writing the sorted output buffer to the disk and reading again, later identify all the tuples for both relations that have this value C equals C, which is that's what they did here in this case, this step. So the cost in this case equal to what here? 3 PR plus PS. We get rid of the writing and reading again in this case, right? In order to do that, you have to have this condition here, because I want to sort R and S at the same time together using the existing number of buffer M. Okay, so if M of these numbers satisfy this condition, yes, you can use advanced sort. Otherwise, you cannot use advanced sort. Okay, clear. The other algorithm is called the index-based algorithm. So in this case, what if we have an index? Can we use the index in order to try to compute the join algorithm in this case? Yes. Well, let's go back here first. So index-based algorithm that's useful in order to perform the selection operation that we did before, but in order to access the data, but it's going to help us also in order to perform, let's say, the join algorithm, or implement the join operator, and hopefully come up with an efficient implementation in this case. We do have two different types of index here. One of them, the cluster index and non-cluster index. I have a minor definition, different than the one that we covered before here. So an index here, where all the tuples with the given search key value appear as a few blocks as possible, we call this one the cluster index. Okay? One relation can have one cluster index, but multiple non-cluster index. So let's give you an example in order to just clarify what I've said here. Assume that we have a cluster index. An index can be built based on a specific attribute A. Okay, so in this case, in order to access specific value A1 here, we're going to have a small number of discrete operation in order to achieve the data that's stored in A. Because why? That's what the definition that we did before when we talk about the cluster index. The way that index data will be stored in the index is going to be similar to the way that the data is going to be stored in the disk, or lay out the data on the index onto the file, right? So if you have A1, when you access A1 here, we're going to have access, say, one or maybe fewer blocks in order to get all the tuple that contains the value of A1 equal, or the value of A is equal A1 here. Okay? This is a true mean clause. So in other words, in order A1, you are not going to find the data, or the data can be stored in the relation R something like this. A1 here, and maybe A1 here, then A1 here, yeah, and A2, then A5, A3, something like this. Otherwise, in this case, that means in order to access A1, I'm going to say A1 is going to be here, then might be here, A1 here, and the data here, A2, then A3 is going to be, for example, here, A5 here. This is not going to be cluster index. It's going to be uncluster. So cluster index, the data that the way that you use to sort in order to create the index is similar to the way that it's going to be sorted, or the data can be sorted or stored in the disk. So that means we're going to have a list number of discrete operation in order to access the data. Okay? And the common way, the example of this case, if I'm going to sort the data based on the attribute A in the relation R. Okay? The non-cluster index in this case, that is not cluster. The way that sort to create an index, or sort the data in the index, is completely different than the data that you're going to lay out in the disk. So that means you here, every time you try to access the data, you have to tell me exactly where the tuple, where the data exists. Or in other words, we give you an example last time. We said, for example, the data, in order to store X value 1, 2, 3, when you try to access one in the disk, 1 is going to be stored here, 2 is going to be stored here, 3 is going to be stored here, 4 is going to be stored there, 5 is going to be stored here, so it's going to be confused. The way that stores the data on the disk is completely different than the order that you use in order to build the index. So that means in this case, you're going to perform too many discrete operations just to try to achieve the data. Or in other words, the data is scattered everywhere. Okay? So first I'm going to show you the algorithm, join algorithm between two relations, R and S. Okay? And in the case that either going to be indexed in the relation R or S. So we do have an index. How can we use the index in order to find out the matching tuples? Remember what we did last time, we tried to find the best way in order to find the matching tuples. Reduce instead to iterate over every single tuple from the relation R. Then you try to find a match with every single tuple of the relation S. Try to find a way in order to reduce the number of the matching tuple, the number that or discrete operation that's required in order to find a matching tuple. So let's see how can we use the index in order to achieve this goal. Assume in this case we're going to perform the the join algorithm based on, or the join attribute is going to be based on the attribute C. Okay. And assume that we have two relation R and S, and the relation S is going to have an index based on the attribute C, which is the one used in order to perform the map join algorithm. So in this case, I'm going to read every single tuple from the relation R, okay? But one block, of course, when we try to access the relation R, we access this one block twice, okay? Fetch a block from the relation R. For every single tuple from this relation R, you need to consult or look up for the index. I'm going to use the s.c index. This index is going to help me in order to find out which is the portion of the data in the relation R, possibly, or they're going to have, let's say, matching value for the value C. Okay, instead we have the X of the whole the relation S, I'm going to X only a portion of the relation S. Yeah, I've said R, no, S in this case. Okay, so for every single tuple, C here, I'm taking a look at the attribute C using the index, look up, the index is going to tell me, for example, you have to access, say, block 1 or block 16 or whatever, okay, where the data is going to be there. Once you fetch these blocks, read them, then after that, we need to output the pairs, okay? So let's take a look here. The result diagram is going to illustrate what we try to do here. Remember, this is cluster index. So the join algorithm scans the relation R once, so we have to access the relation R once. And for every single tuple from the relation R, you need to join to the tuple with the S. How can you perform that? I'm going to look up in the cluster index, s.c, and the cluster index is going to tell me this is the portion of the data, or this is the number of blocks that you need to retrieve from the data. Okay? Here we assume, or we can come up with like estimation, how many blocks we are going to achieve from the relation S. We're going to say it depends on the unique or distinct value for the attribute C that's stored in the relation S. So for example here, if C is equal 1, so this means all the value of C is equal to, has exact value, same value. So in this case, you are going to read the whole relation S, right? This is the number of blocks that you need. Because you're looking for C equals specific value, since we have only one unique value, this estimation that we have, we're going to read the entire relation. If the unique or the number of tuples or the distinct value for the attribute C is equal, for example, 2, that means we are going to read the half of the tuple of the relation S. Right? So that's for every single tuple, this is the portion of the data that we need to read. This is in the case if we have a cluster index on S. So that's explanation. Why? Because like it looks like, we do have like number of fragments and can be divided by, or denoted by, or specified by how many distinct value for the attribute C in the relation S, which is going to give me how many blocks. Again, if one unique value, then we need to read the entire relation. If, for example, 100, that means we need, this is just estimation. This number of blocks that we need to have, number of blocks PR divided by 100. Okay, this is in case of the cluster index. Good. Good. So we can put things together. This is the formula that we're going to use here. So what we did here, if we go back to the algorithm, let me go back to the slide here. Yeah. So I'm going to read the entire relation R, if the index based on S. So we'll read the entire relation R. It depends on the relation R. Whether the relation R is clustered or not. If the relation R is clustered, this means required for me to have PR. If not, that means I need to perform TR. Alright? Plus. That's the cost for reading every single block of the relation R. Then after that, for every single tuple, do you need to read this tuple? No, it's available in the memory. So there is no cost for reading this tuple because it's already counted here. I need to perform what? I just see read specific number or portion number of blocks from the relation S. Yeah. So in this case, if the cluster index that we have, I'm gonna say for PR and for every single to the relation R, I need to have a specific portion of the data or number of blocks is gonna be read every time. So the number of blocks is gonna be divided by PS over V, S, and C. Right? With how many blocks I need to retrieve here, it depends how many unique values you have or distinct value are stored in the relation for this attribute. Why TR? Because here for every single tuple, I'm gonna read PS divided by V, S, and C. Alright? Since we have TR tuples, I need to perform this operation TR times. Why did you include the cost of reading this tuple? Because I already count this one. When I scan this relation R, they didn't be available in the disk, in the memory, so I can use it. So this is the formula here. You can simplify the formula that since the TR multiplied PS divided V, S, and C is larger than the number of blocks, so either you can use this one, or you can say maybe almost the result is going to be equal to this value, or approximate commutation. if you try to come up with the approximate number of discrete outer operation in this case. If the relation R is not clustered, that means the only thing different here, when this is the cost to read the relation R. You see? If the case, the index is clustered. Clear? Okay. So what if the index is not clustered? Oh, I'm going to scan or read the entire relation R. Assume the index is based on the attribute C in the relation S. So we are going to, in both cases, you have to read the relation R. Okay? Then for every single tuple, you need to retrieve a portion of the data from the relation S. And the portion going to be defined here in this case is not PR divided by VC, SC, and S and T, distinct value, number of distinct values of attribute C in the relation S. No, it depends on what? TS, number of tuples. Because the data, since this one is not clustered, it depends how many unique values that we have and how many going to be stored here. How many values going to be stored in the disk here. If we have only one unique value, that means you have to, all the relation are S, it's going to contain the value of C equals specific value or one single value. So we have this, remember, the estimation. So I have to read the entire thing. If you have only two unique values for relation S, that means you're going to reach or read, you say, half of the number of tuples that you have. And again, it's TR because it's unclustered. So one tuple is going to be one block and another tuple is going to be another block. Of course, under the assumption that we did before. When you fetch one disk input out operation or perform one disk input out operation, when you read one block from relation S in this case, since it's an index and a cluster, we assume that we are going to find only one tuple that satisfies the condition that we're looking for. Okay? So assume that one tuple S in each block is going to be right here. So the same formula that we did before, I need to perform scan relation R once. I need to compute the number of tuple relation R, multiply the number of blocks that I want to read from the relation S. And here you need to do the same thing here. Well, how the cost, how do you estimate the cost of reading or scan the entire relation S? Sorry. So in this case, it depends on the clustered or not. If it's clustered, that means I'm going to use PR. If not clustered, that means you have to use TR. Okay? Then for every single tuple here, you need to use or read this portion of the data. Since unclustered index, it's going to be TS divided by VS and T. So the difference between the cluster index or non-clustered index here, I want to use PS. This is the only difference here. Non-cluster index, you have to multiply, or this is the portion of data defined, or number of tuples defined, or number of blocks you need to achieve. Since unclustered, I need to use the TS here. Okay? So the question here, when we're going to use the index join here. So if this is a database, one option for the database management system, we're going to see what kind of relation do they have. Whether they have one relation that's going to have like, or the large relation that has an index on the join attribute. And the other relation, one of the other relation, other part of the operand of the join algorithm, or the join operand here, it's going to be like a relation that is very small. So in this case, when you have a join R with S, assume that the R is the larger relation, and this is the smaller relation. And we are lucky, we do have an index based on the join attribute in the larger relation. So you see that in this case, I use the smaller relation. For every single tuple, I need to use the portion from the larger relation. So that means we're going to reduce the number of discrete out operation because we're going to use the index, and index is going to help us in order to reduce the number of discrete out operation in order to satisfy the condition or in order to perform the task. Okay, let's go with our numbers. Assume that we have R and S to relation, and now we said the index is going to be based on the joint attributes, and this one going to be belongs to the relation R. Okay. Here, ignore that the two levels, etc. I wasn't planning to give you like complicated example. The one that we have a multiple level of index, and I wasn't planning to assume that the index is not going to be fit in the main memory. So there is a cost how to access the index in order to figure out, find out, when you perform lookup for the R.C on the index. Actually, in this case, S.C on using this as input to this index. And you need to perform the lookup. So I was planning to ask you to compute the cost, but ignore this one. For this class, and even the exam, and if we give you something similar to this one, I'm going to say the index is going to be can't fit in the main memory. So you are going to ignore the cost associated with the index, okay? Assume the relation S is contiguous, okay? And or sometimes you're going to say, give you some details that maybe you don't need. Do you need data, whether data is going to be sorted or not sorted based on relation S here? No, we don't care, because we don't require the data to be sorted. Only thing that here we need to know whether the index is going to be clustered or non-cluster index. Okay. Assume that R.C index, as I mentioned, is going to be fit in the memory. So fits in the memory. So done. In this case, there is no cost. We're going to perform. We'll try to associate with the lookup for the S.C on the index. So the cost is going to be the number of discount operations. Can be read the relation S one time because it's contiguous, is clustered. For every single tuple of relation S, I need to specify, since the index is unclustered, so it's going to be TR divided by VR and C. What if I don't have the value of R to C, the distinct value of the attribute C in the relation R? So we have other ways we can estimate that. Yeah. And remember, the cost here, I'm going to use the same numbers that we used before, the example. We have the number of blocks, PR or PS is given 500. And let's say PR, for example, would be 10,000. And the TR is going to be 1,000. Remember, this is the question that we have. Actually, the opposites, yeah. TR is going to be 10,000. And BR is going to be 1,000. This is the example that we had before. Okay? So you need to, for every single tuple of relation S, you need to do what? You need to look up the index or prop the index. With the cost, there is no cost. We assume that all the index is going to be available in the main memory, can fit in the main memory. So if there is a match, we need to read R tuple, which in this case for every single tuple for R, since it's unclustered, you need to perform one disk and without operation. So put together. So I have two cases. First, if you don't know for the case one, I don't know, for example, the VR.C, or maybe you have more details I can better estimate, how many tuples I need to retrieve. Assume that we have, as we mentioned, we have R and S, both of them, they have C attribute. In this case, we said that R.C is a key here. So the primary key here is C. Yeah, and here it's going to be foreign key, C. Okay, so in this case, if you have this foreign key, you are looking for, you're going to use S.C in order to search using the index of the relation R.C. So since this one foreign key, and this is going to be primary key, so definitely you have what? It's going to be only have one single value that satisfies the condition that R.C is going to be equal S.C, right? Because again, I'm looking for the index in the relation R, and we have, it's going to be for primary key, so there is no duplicate value based on the value to C here, right? So in this case, we have only expected we're going to have only one match. This is the number of tuples for relation S divided by the VR C. Sorry, number of tuples for relation R divided by the VR comma C. Or what's the portion of data that you need to achieve every time to try to access the relation R. Yeah? Or if we know, I don't have this information, but lucky us, we do have the distinct, the distinct value of the attribute in the relation R. So assume that the value is 5,000 is given. I know the number of tuples 10,000 is given for us. Then assume that we have a uniform distribution. This is our assumption, okay, to simplify the process. And how can we estimate the cost? And you can divide by VR here, TR divided by VR, comma C. Okay, which is going to give you to match or whatever. So it's just to plug the numbers. Here, the first one, if we know that the case that the one R.C is a key of the primary key of the relation R, and S.C, C is going to be like foreign key in the relation S. So in that we have only one match. Yeah, because for every single tuple of the relation S, you're going to find only one exact match in the relation R. So we can compute the cost. And here you have a few questions. Will any of these going to be changed if we have cluster index? Of course, yes. Because in this case, I'm not going to divide by TR, let's say, divide by VR and C. I'm going to use PR in this case, yeah, in order to compute the cost. And the cost is going to be definitely less than. What if the index doesn't fit in the memory? So in this case, we need to figure out a way how can we estimate the cost in order to prop the index. Okay? That's all about the index. How can you use the index using join? Or perform join using index. Now I'm going to show you that how can we use the hash join, perform hash join. Before I do this one, let me show you the first one-pass algorithm which allow us in order to join two relations. which is the simple algorithm that we use. And one pass with the easy algorithm, this is the fast, or of course, if we can everything somehow can fit in the main memory, we can perform or use this one. Or at least we have one relation can fit in the main memory. How can we perform or join two relations? Then after that, we're going to use this one pass algorithm in order to help us in order to compute or order to implement the hash join in general. Okay? So the assumptions here assume that we have, of course, two relations. One of the relations, the smaller one, it's going to be S, just for example. So first I'm going to do what? I'm going to take the relation S, the smaller one, and somehow I'm going to build special data structure. This is special data structure, I'm going to use this one in order as a search data structure. It's going to help me in order to find out. Remember, instead to scan the entire relation R and S, we'll find the matching tool. We need to find any technique, any mechanism that help us in order to reduce the number of discounts out of operation, or to reduce, the number of blocks that you need just to focus on, just to see whether to find the match or not. So we're gonna build this back to the relation S, build this search structure. You can use hash table, or you can find a search tree, whatever search structure can help you in order to minimize the memory requirement, and also in order to help us in order to reduce the number of disks operation. And also we're gonna more focus. You're gonna tell me this is the portion of the data that you want to just to focus. Okay, so we do have two phases. The phase one, I'm going to take the smaller relation. Okay, I do have m buffer. Remember that's given here. I'm going to use one buffer in order to read one block from the relation S. So S, we have the large relation, and I use one block in order to read one block at a time from the relation S. Then I'm going to use the rest of m-1 blocks here in order to build whatever the search structure that you want. If you wanted to build hash function or hash table, so you can take every single tuple for relation S, compute the hash value based on the whatever attributes they use in order to perform the join, which in this case is example C, and this is going to tell you where you're going to hash this source key or this tuple, right? So we do have, in this case, we use m buffer, one to read the data, one block at a time from the relation S, the smaller one. Then the rest of m-1, we're going to build what is called the search structure. Okay. Then the phase two, what I'm going to do here in the phase two, I'm going to keep the m-1 structure going to be available in the memory, still there. Then I'm going to reuse the block that you use in order to read every single tuple from the relation S. So here I'm going to use this one, take the relation R, the larger relation, read one block at a time. Yeah, use this block. Let's use this one here. One block at a time for every single tuple. I'm gonna prop or use lookup using the whatever the search structure that you built. Okay. In this case, if we use hash, I'm gonna perform the hash value based on this the join attribute C, and this one the hash is gonna tell me where the block that I can find the data. Maybe I'm gonna hash this one. This one available in the main memory. Since I'm gonna use hash, I need just to make sure that the tuple they're matching. Yeah, must be R.C is equal S.C. If I'm using search, binary search, it's going to be whatever going to show me the block. Then you can just make sure you need to perform the search in order to make sure that you have the match tuple. Then after that, I can produce the result. That's what it's called. How can we use the one pass algorithm? Why it's one pass? I'm going to use acceleration S one time, and also the relation R one time. Yeah, this is the most efficient algorithm that you can come up with. This is just description of whatever I've said right now. Just summarize what we did here. Take the smaller relation, okay? Read one block and use the m-1 in order to build, let's say, the search key, or this data structure, or whatever search structure that you come up with. And again, it might be hash table or binary search tree, or whatever search tree or data structure data structure that help you to search faster in the data, a more efficient way, actually. And then after that, I'm going to keep the m-1 still there. The search source is going to be available, and you use the block that you use for every single tuple for relation S. Now use every single tuple for relation R. Then use this hash the same way that you use if they build the search structure, just to search, just to see how can you figure out, find the data they're looking for. If you find match, then you just print out, display, or concatenate the result. Okay, and this is the diagram show us what we did here. Okay, so there's the need to go over this one. The only thing you need to specify here, we're going to use the smaller relation in order to help us in order to build whatever search structure here. Okay? So what's the number of disk input out operation in order to perform this operation? Sorry, and this is the phase 2. In the phase 2, remember, the n-1 buffer is going to be available in the memory in this case. Must be there. Yeah. So what's the cost of this operation? The cost of the operation is going to be R plus PS. Do we have any memory constraint here? So take a look here. You need to use what? Somehow, the smaller relation must fit in n-1 input buffer, right? Because when you build the social structure, this one is somehow going to store the data there, the tuple there. If you use, for example, hash table, so when you hash the value, you're going to have give me, for example, the entire data relation is somehow it's going to be stored into that buffer. Yeah? Someone said, can it store only the hash value, then pointer to the data? No, that means you require from us to perform another disk input out operation in order to fetch the whole data or the rest of the table or the tuple that I need. Yeah, I don't have enough buffer in order to hold that result. So in this case, when you hash the value here we are going to store the entire tuple from the relation S. So somehow the whole relation S is going to be stored in the social structure that we have, that we built here. So the cost here, the constraint here, the value of M must be greater than or equal the value, say, the number of blocks of relation S, and also we need to have a plus 1. Why plus 1? Because you need to store the somehow M is going to take BS, the whole block or number of blocks that contains relation S, plus the plus 1 that you need in order to use as input buffer in order to read one block at a time, in order to process the data from S and from R. Okay? And this is going to be the number of blocks or number of tokens that you need to required in order to use one pass. So in order to use one pass, if I say, for example, you need to join R with S, the simple thing you can figure out to take a look here, can I do this one pass? So in this case, you need just to check which is the smaller relation, R with S for example. I check here with the available buffer M is greater than PS plus 1. If yes, then you can use this algorithm that we have here. If not, that means we're going to see how can you use the 2-pass, which is the one that I'm going to show you. Or maybe you can use merge join, sort, or maybe use index join if you have index, etc. Okay? So in this case, I'm going to do the following here. The first step, I'm going to use, by the way, M buffer, one at a time. I'm going to use one from, let's say, M-1 in order to build whatever social structure. In this case, I'm going to use hash function. So I need to build the basically hash table. Okay, and here I'm going to use the other input buffer in order to use one block from the relation R. I will perform the same operation S, then after that in R. Let's do one at a time. Focus on R first. Take read every single block from the relation R. For every single tuple, you need to compute the hash function over the join attribute. And you are going to hash this hash value, or the hash function you're going to produce or use is going to what? It's going to compute or sign the value or compute the value that allow me in order to have M-1 bucket. Okay? So in this case, bucket 0, 1 up to M-1, minus 1, of course. Okay? Or assume the bucket is going to be start from 1, it's going to be end up we have M-1 buffer. Alright? So for every time you read the data and store this one block. So I will store the entire tuple in this relation, or this block. If this buffer is full, I need to store this one back to the disk. So this means, it does mean that, we need to hash the entire relation. Sometimes we end up, we have some buffer that can be full. You have to store whatever the content of that buffer, the disk, then after that, or free space, then after that, starting caching again to that buffer. So when you continue this one, I will do this one for the relation R. Done, yes? I'm going to use the entire M again. I will do the same process for the relation S. One block is going to read one input buffer is going to read one block or a block at a time from the relation S. Compute the hash function based on the join attributes, and it's going to be hashed to the M-1 bucket. And here I'm going to use the exact hash function that I use here in order to hash the search key, for example, or the C value in the relation S, with the similar to the hash function that I use in order to hash the C, or based on the C attribute in the relation R. Must be the exact hash function. Okay? So if I use the same hash function, and the same thing, store here, 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 if this buffer is going to be full, reflect this one on the disk, then continue our free space for the next tuple, or maybe the other tuple is going to be inserted in this place. One interesting property here, since I'm going to use the same hash function, and I'm going to hash based on the same attribute. So if we do have one tuple, and let's say small r, okay? If you have one tuple belongs to the relation R, and you have one tuple belongs to the relation S, okay? And this tuple, for example, the value of C has, for example, value 5. And here for this tuple, the value of C tuple attribute is going to be equal to 5. So if they have the same value, when you compute the same hash function, what's going to happen here? It's going to be hashed to the same bucket, right? Because I'm going to use the same hash function based over the attribute C. If the attribute C in one tuple relation R and S, both of them, they have the same value, they're going to be hashed to the same bucket. Okay, so what's the benefit of this one? I should give you, for example, both of them equal K1, for example. So C K1 is going to be hashed in this one. Okay. When you try to perform, this is the phase 1, by the way, for multipass. When you finish this phase, so in order to find the matching, we'll perform the join here. It makes sense to us to do what? Since I know the attributes with the same value can be using the same hash function, can be hashed into the same bucket. So in this case, I'm going to perform the join. I didn't need to join all of them together. No, I'm going to take corresponding pairs of the bucket that must be considered together in order to find or examine together in order to find whether they have any matching or not. In other words here, in this case, in order to find the match between this bucket, this bucket, and this bucket here, I need just to compare both of them. So that means if there is any common attribute of the value of C, it's going to be has the same value, or assume this value is going to be K2, then definitely going to be find matching in this bucket and this bucket. So this is the only thing that you need to compare. I need to compare this with this. Then after that, I need to compare this bucket with this bucket. Then after that, this bucket with this bucket, and etc. So instead we have the whole relations, we can process the equality join tuples of the join operation by only examining the corresponding pair of the buckets alone. So what do you mean in this case? Looks like we have the one pass merge join in order to join the corresponding bucket together. So this is the phase 1. Clear what's happened here? Why you need only to join or examine only the corresponding pairs of the bucket alone in order to find the matching? Because based on this property. So this saves us time. And remember the goal here, try to reduce the number of discounts out of operation. And also when you perform the join, I don't need to consider the entire relation. Now we find a way or mechanism which allows me to say the only thing you need to consider this portion of the data, or this portion is say a pair of the buckets alone in order to consider whether there is a match or not. So I can move this to phase 1. This data can be stored in the disk. Okay. Now in the phase 2, I will consider, remember what we did R with S, join with S. When one pass, we go with a smaller relation, use M, we are going to create a search, let's say, search structure based on M-1 bucket, and we use the other bucket in order just to use one block from the relation S in order to build this search index or the search structure. Then after that, I will keep the M-1 going to be available in the memory with the search structure. I will reuse the one input buffer in order to reach one block from the relation S at a time. At the time, then you try to find the match or search or prop within the M-1 in order to find the match with the relation S. Okay, so here I'm going to take this one, and this one I'm going to perform, let's say R1 join R2, S1 using one pass join. Then R2 join with say S2 using one pass, and the second and the third with the third. We'll reduce the size with it. How can you perform that? So now, second phase. Oh, the second operation, sorry. It's the second operation. So here in this case, I'm going to do, in the first one, that's what we did here. Sorry, let me go back here. That's what I'm storing. Now I need to build the social structure, or the whatever, the binary search or data structure, or the user will perform the search. Then after that, find the match. So in this case, I'm going to use SI, which is going to be, assume that the relation S is going to is the smaller relation in this case. So I'm going to use the sub blocks that I generated from the previous step. For each of them, I'm going to take one block or one input buffer, and I'm going to build to say whatever the search structure. This is exactly one pass. Then after that, he used the input buffer in order to read the data one at a time from the relation R. Then try to use whatever the value that you use in order to perform or build this search structure. Again, if you use a binary search or maybe use hash table, that means you have to use the hash function. It will tell you where's the bucket that you need to access for n-1. This is only for this operation. It's going to be involved only one chunk from the code here. Or you say it's going to be only the corresponding pair of the buckets. This one with this one. Then after that, this one with this one. And that's after that. Okay? Which makes sense. Because if it's having the match based on the value of C, especially for that quality, that's what we use in the hash, since you use the same hash function, definitely whatever. If there is a common value, it must be, as example, K1 must be in this RI here, and where they say S, whatever the value of S here, J or I here. Okay? So what's the cost here? You are going to read the relation R. You are going to write n-1 buckets total in the relation R. In the disk, yeah, after you compute the hash function. So hash every single tuple in the relation R or S is going to be into n-1 bucket. Then after that, we are going to store the whole n-1 bucket. There is sometimes it's going to be overflow or twofold. That means sometimes you get to fill this one to fit or say store whatever the content of data block in the disk. Then after that, we're starting filling with data. So here I'm going to read the relation R one time. This I'm going to use BR. And the same one for the relation S. Okay? What if the data is not clustered in this case? This is for the writing. What if the data is not clustered? So if the data clustered, that means it's going to be BR, the cost, and 2BS. If the data is not clustered, it's going to be TR plus BS. BR, sorry. And if the data S is not clustered, the same thing. Yeah? Because when you read one block from the data R, one input, it's going to say, we end up, we have what? Only one tuple belongs to this relation. So if you want to read the trial or fill this block with the data, that's means you're going to perform multiple number of this kind of operation in order to fill one input buffer. Right? When you store this one, when you hash them, now it's going to be clustered because you're going to hashing the value. Going to be, for example, for the block bucket 1 or 2, this is going to be belongs always when the tuple is going to be belongs to the same relation, so it's going to be end up we have a cluster. Okay? The cost in order to perform phase 2, within this case, we talk about the phase 2, they will perform, let's say, join based on the corresponding pairs of the buckets. Yeah. So I'm gonna have the B relation R plus I'm going to read the relation S. So the total is gonna be 3BR plus 3BS, or let's say easy 3BR plus BS. And this is the cost in order to perform the index using the hash. Is there any constraint? Yes, because we do have a constraint based on the one pass, where we perform pass between two relations. Remember, we said that the PR of M must be greater than or equal PS plus 1, because I'm going to somehow store the relation S or the smaller relation in the main memory. We want to keep from the phase 2 the n-1 bucket must be available in the main memory, which is the one that corresponds to the smaller portion of the to say the bucket corresponding to the smaller relation. Yeah. So here we can come up with a formula. We can say, okay, the minimum between the BRI and SI. Yeah. Remember, we have a chunks here. This relation R and S. Consider corresponding pairs are going to be joined together. It's going to be examined. So in this case, I need to have that what the BRI, what's the size of this, and what's the size of this. We also have an assumption. We can say the hash function that we use is great. It's going to be evenly distributed, I mean, the attributes among all the buckets, evenly in this case. So if we have, for example, BR, and we need to distribute this one among n-1 bucket, say buckets or buffers, so we can divide them. Yeah. Substitute these numbers, or this formula here. BRI with this value and the BSI with this value, so we end up we have the M is greater than or equal the square root between the minimum between the BR and the BS plus 1. Which one, regardless which one is going to be smaller. Always we focus on the smaller. This is, I mean, the requirements in order to use here and to pass. So if we have to check the condition, if we pass, that means we can use to pass. Okay. So give me an example. Assume that the relation R and S is contiguous. It is unordered in this case. And in order to compute the total cost, you 3 multiply and the cost with the relation R and S. Someone is going to say, why give me this unordered? This is, I mean, sometimes they give you something that you are not going to use. Here, I don't care whether the data is sorted or not because my algorithm is not going to care. You don't care in this case, yeah. I only care whether it's going to be clustered or unclustered. Okay,